One. Thank you very much for joining us today for another Autodesk University session. We have a team of 4 speakers today for you, and we are going to be speaking about bridge inspection using aerial robotics. And what we're going to do today is we are going to introduce you an end-to-end automated workflow on how robotic-driven inspection can be done on all kinds of infrastructure systems and specifically bridges. My name is Mani Gopawar. I am Chief Technology Officer and co-founder of Reconstruct. I'm also a professor at the University of Illinois. And for the past 15 years, I've been working on computer vision and machine learning for construction and operation monitoring in the built environment. Today, I'm joined by 3 experts on bridge inspection. And I'm going to ask them to join me in introducing themselves to you. Our next speaker will be Nita-san. Nita-san, could you please introduce yourself?
Hi.
Wonderful. So Nita-san has joined us from Ministry of Land, Infrastructure, Transport, and Tourism in the country of Japan. We also have Morikawa-san. Morikawa-san?
Yes.
Wonderful. And Morikawa-san is joining us from Public Works Research Institute, affiliated with National Research and Development Agency in the country of Japan. We also have Fukuchi-san. Fukuchi-san?
Hi, nice meeting you.
Wonderful. And Fukuchi-san is with Autodesk. So the team of 4 of us will be speaking to you on this topic. But before we get into the topic, I want to share with you some statistics. Over the past few years, a new opportunity has really formed to rehabilitate existing status of our infrastructure systems in the United States. The current government has been tossing around the idea of allocating budget to improve existing conditions. And this is a really important issue for us because when you start looking to various types of infrastructure systems that we have, there's a whole lot of room for improvement. More than 75% of the bridges that we have today in the United States are at least 40 years old. And if you look into their status, reports that are coming out from Federal Highway Administration and a lot of departments of transportation are showing that almost 10% of these bridges are structurally efficient. I'm calling in from the state of Illinois, and in the state of Illinois, we have a little bit over 2,200 of these bridges. So the situation that we are facing with is quite risky in terms of how we are operating our existing infrastructure systems, particularly when we look into what kind of traffic that we have. Daily, on average, we have roughly around 188 million trips that are being made on these bridges. And of course, we would need substantial amount of funding to rehabilitate these existing infrastructure systems. That number is slightly over $120 billion. So it doesn't matter how much we start allocating immediately. What it means is that we need to figure out which one of these bridges are in dire need for improvement immediately so we can prioritize budget reallocation. So what that means is really for preserving performance and in making sure we have safe operation on our existing infrastructure assets, we need to have inspection. Inspection that is timely, so it provides information when we need it. It's effective, so it actually does improve the process and addresses the specific issues that we have, and it's accurate. So we don't need to go back and redo the inspection over and over. But when you look into the process of inspection today, you would see 4 different pain points associated with the process. One, our process is generally very expensive and destructive. Many of us who are involved in the process of inspection, we've seen special equipment that are being used, and obviously it has an impact on traffic, it has an impact on manpower and resources that we're using. Many times they require closure of the road, and of course logistics is always #1 issue when it comes to these inspections. The process of documentation for long has remained to be very time consuming when you consider that a lot of inspectors have to be, in arm's length away from the infrastructure. And because of the time limited aspect that we have, and because we can't get all of our experts to visit these sites, oftentimes the assessments that we have can be inconsistent. Over the past 5 to, I'd say almost a decade, there's been quite a few departments of transportation in the US have led the charge in coming up with the requirements for improving this process of condition assessment. And out of that process, there are really 4 top goals that are being highlighted. There's always a need for new procedures that can be easily standardized in terms of how you're documenting existing conditions, how we are communicating defects that we see and we analyze, and how we can follow up on recommendations that are being made by our inspectors. Oftentimes, when we speak to Department of Transportation and with our colleagues in Japan at the ministry level, there's always a need for a unified system that everyone, no matter where they are, they will be able to get access to the information, store it securely, and be able to retrieve that information over the life of that asset. Of course, many issues that we spoke about in terms of documentation, how fast we can do it, and the accuracy of the process is also pretty important to us. And on top of all that, we really want to make sure that every stakeholder engaged in the process, from that inspector to the owner of the asset, would have all the information that they need at their fingertips so they can make the decision at the right time using this actionable insight. So what is the opportunity? Over the past decade, there's been a surge of visual data that's already being captured on all kinds of infrastructure assets. Whether you're owning and operating a bridge, whether you're engaged in the railway industry, whether you're involved in tunnel construction, there are all kinds of these images and videos being captured. Sometimes we see photo light captured with cell phone devices. Sometimes there are cameras that are being mounted on inspection cars, time-lapse photography, action cameras, and drones. Drones have been really transformative. And of course, laser scanning. So as a team, when we started working on this concept almost 10 years ago, we started looking to how we can expand on the value of visual data that we use for coordination and communication as the basis of our inspection. Among all these form factors of capture, the one that's been really transformative have been the application of drones. Camera-equipped drones are really easy to operate, and we've seen a surge of their application, not only in the US and Japan, but also around the world in many of the projects that we engage in. In fact, Minnesota Department of Transportation, with Collins engineers, they actually published a report that shows when you use drones, you can immediately have cost savings associated with minimizing exposure of your inspectors to the infrastructure and the time that they have to spend in the field using special equipment. So obviously it's faster and cheaper. It reduces the need for all kinds of access and control measures that we have to bring in from a traffic perspective. And when you supplement that with a cloud-based analytics platform, the requirement of having the engineer to be really out in the field would be dramatically reduced. So with all those values, we started working on this concept. And back in 2016, almost 4 years ago, we teamed up with Japanese Ministry of Land, Infrastructure, Transport, and Tourism to look into robotic-driven visual inspection of infrastructure assets. So with that, I want to pass it on to our co-speaker, Nita-san, to speak about their story of how the government of Japan came up with this initiative. Nita-san?
Hi, hi. My name is Yasushi Nita, and I am in charge of policies regarding the introduction of robots at MLIT. Thank you very much for having this opportunity to give a presentation here today. Since the time is limited today, so I'll focus upon the robot for the inspection of bridges. Next slide, please. The government of Japan set up a new robot strategy in 2015 that aims to showcase Japan to the world as the most advanced robot society. This new strategy is intended to promote the development and introduction of a wide range of fields, including manufacturing and related service, agriculture, nursing and medical care, social infrastructure, disaster response, and construction. Next slide, please. This slide shows the overall pictures of the project. We recruited inspection robots for 3 years and verified their functions on the actual site. For bridge inspection, we plan to certify the performance of the robot for the requirement. In addition, I'd like to propose a new inspection method using a robot to achieve more efficient maintenance management. On-site verification, various types of inspection robots were proposed, exceeding 100 technologies. Next slide, please. On the other hand, the infrastructure of Japan is aging, and the working population is decreasing, especially in the construction industry. In the next 10 years, a serious labor shortage is expected due to mass retirement. Retirement of the people 55 years and older, which accounts for a third of the current labor force. Therefore, we think that increasing productivity is an important issue. Next slide, please. This photo shows the bridge inspection work in Japan. The bridge pier is 50 high. The box girder also has a height of 10 meters. A close visual inspection is required for all parts. Number 1 picture shows a rope access status. Number 2 picture shows the inspection inside the box girder with ladder. Third picture shows inspection with a large bridge inspection vehicle. Next slide, please. Sorry. Next slide, please. I will show the most important use case when evaluating inspection robot. In the present situation, the person creates a record after the inspection staff has finished and visual inspection. Inside this red box shows a use case that uses a robot to create a damage record. The lower column represents a use case in the near future based on the robot inspection result. The person will be screened for a range of visual inspections. At this time, the bottom technology doesn't exist, but we expect it to happen in near future. Next slide, please. MLIT have started to include AI budget from 2018. Inspection robots, unlike people, get large number of photos and videos. AI can process faster than people to decipher large amounts of image from robots. In order to improve the efficiency of robot inspection, we aim to achieve high detection efficiency by AI. Additionally, we will develop supervised data with input of experts, and we will promote the installation of evaluation system. Next slide, please. This slide shows platform in which the development of inspection robot AI is promoted. The blue highlighted parts show what MLIT will implement. Namely, there will be inspection data to be developed. Data set for AI inspection to be established, and validation system will be put in place. The yellow part on the right hand side show how the development of robot AI can be supported by the use of disclosed data. Next slide, please. Thank you very much.
Thank you, Nita-san. So as you just heard from Nita-san, and same applies to Murakawa-san, a lot of these problems are exactly the same as what we experience here in the US. So when we started our discussions with MLIT roughly 4 years ago today, we were really excited that government of Japan has come with a new initiative to very seriously invest in R&D that can lead into robotic-driven inspection. And as part of that, not only was it important to have the technology, as Nita-san mentioned, but it was also important to have the right workflow. We cannot take the entire industry to transform their practices overnight. Rather, we need to have a strategy and a process on how we can promote the application of robotic-driven inspection first, and eventually tapping into the power of AI to enable automated defect detection, as an example. So with that in mind, we started partnering with Murakawa-san back in 2017, and we had the opportunity of meeting with Nita-san almost in 2018 to start piloting our technology roughly 4 years ago for visual and virtual inspection. Our platform Reconstruct is a unified system that provides that process of improving inspection in terms of how we are documenting defects, the timeliness aspect of our process, and the accuracy associated with the performance that we have. So broadly speaking, Reconstruct platform builds on Autodesk solutions. We've been recently featured on Autodesk Forge blogs because this technology really builds on Forge model derivative API capability in addition to parts of the Forge viewer. Our solution is also very tightly integrated with your BIM 360 solutions. And what that means is now all kinds of visual data that we refer to can be brought into a system so they can generate a historical record of any of your infrastructure assets. Our platform sits on Forge, and what that means is that you can also bring in your design information in 62 different file formats. So we have some extra file formats. Whether you're looking to your InfraWorks, Revit, Civil 3D, Navisworks file, that can all be, or even 2D drawings, that can all be brought into Reconstruct, where that would be laid against the reality capture. So basically images and videos would be automatically transformed into 3D models with a unique engine that is outside of the Forge box. So it's Reconstruct engine. And then it would be overlaid with the design information. And once inspection is being done, every single issue that is being documented in the system can also be transformed into a work order. So you can actually tap into scheduling capability and create a work order immediately out of your inspection process. This entire system is accessible through the web and also mobile phones for individuals who are out in the field, whether it has to do with the work tracking or the visual documentation. So again, when we started looking to this in terms of scaling, we immediately realized the number of bridges in the country of Japan are very comparable to the numbers that we have in the US. And what that means is that probably there are many different owners, and each owner, contractors and consultants that are working for them, they leverage different modalities of capture. Sometimes they take still pictures with their phone, sometimes maybe 360 cameras, like the picture that Nita-san showed, somebody walking into the girder box. And many times these days, we can tap into the application of drones, webcams, and scanners. So we wanted to make sure that we can come up with a platform that is agnostic to how visual data is being captured. Of course, with guidelines, but agnostic to make sure every infrastructure asset can be documented. Going back to those needs, we wanted to make sure we have a web-based system that makes the data accessible to every party that's engaged in a project. All data, whether it has to do with the visual data, procedures, manuals, reports that are typically byproduct and or the product of the inspection process are correlated and linked. And everyone who is on site and remote, especially with COVID-19, they will also be able to get access to the information and interact with it. So this will be a system-wide analytics capability that you'd be able to tap into to document your assets of interest, let's say a bridge. And every 2 years, every 5 years, when you're coming back, you'll be able to generate a new model, automatically have the model aligned against the previous one. So you would have a 4-dimensional reality model, fourth dimension here being time. And so that report can be organized around work locations automatically in a 3-dimensional scene. So with that in mind, we extended the capabilities of our engine that can really take in unlimited amount of images and videos, and the form factor doesn't really matter. As you'll see in our handout, this engine can take in, some drone pictures in addition to maybe some pictures that would come from a 360 camera or a combination with a video. All that would really result in a three-dimensional scene, a point cloud and a mesh model, and also 2-dimensional ortho photos. orthophotos that can show you top-down view, bottom-up view, side view, or you can create cross sections to generate these views. And what that means is that now you can click on any location you desire. The system would automatically bring the most relevant image. And now you would be able to dive in and perform your measurements in a three-dimensional scene from that picture of interest that you're looking at. So let me show you this video so you can actually see how the system really interacts. And I'm going to pass it on to Fukuchi-san in just a moment. So what really happens is for every bridge, we provide guidelines for inspection. Under the bridge, sides of the bridge, any location of interest will be documented. All these images are being processed into Reconstruct engine, and they automatically generate that point cloud, the mesh model, and the orthophotos that I referred to. So now the inspector can actually log into a visual system, and within the visual system, you can click on any location you desire, and the system would immediately bring in the most relevant image for you. We've actually posted some guideline in our handout that we developed this technology, making sure the measurements are really accurate. The requirements for inspection accuracy is usually millimeter or sub-millimeter. And what it all means is that we also need to make sure markup capabilities are done. So we've tapped into some of the Forge capabilities to bring that data into the scene. The challenge was really interacting with the point cloud images and design data, so some novelty on what is being built on top of the Forge viewer here. So all that data, again, enables you to perform your measurement in a 3D scene. When you perform your documentation, you can create custom forms. So you can say who's created that inspection log, what is the XYZ if it has GPS data, it doesn't have GPS data, and you can have customized forms that can say how many types of defects have been detected, what type it is. In the case of MLIT, 26 different types. And then you can also associate severity. There's a console that you can document information associated with that. So it's basically inspection logs, recommendations on how that issue can be addressed, or it can be a platform for communication that over time, it really shows you all the logs of communication across various project stakeholders. Once this process is complete, you can also attach reports, manuals. So again, all your inspection data can be localized against one location in a three-dimensional scene, and anyone coming back in the future, they can easily click on that location and that all information comes back. From every issue you document, you can immediately create an activity from a work order perspective. So it really creates that schedule of systems and you're able to use that. So again, pinning would be, you click on a location. If you have a list of, default types of defects that you want to be detecting, you can grade that, and all that system would remain in the platform. So that being said, we worked very closely with MLIT and some of our also partners here in the US to devise a workflow that we can gradually introduce this capability to scale. And this has actually been used on hundreds of projects already. And what that means is we need to have proper guidelines on how visual data can be captured. In the case of MLIT, there are strict requirements of achieving 0.2 or even 0.1 millimeter to detect hair cracks. So the location of images against the structure, viewpoint, all that really matters. Once the images and videos are captured, they can be brought into Reconstruct engine, where it will be automatically processed into three-dimensional points. This is where we tap into the Forge derivative API, where now we can import in 2D and 3D design information. And that's where we very closely worked with Fukuchi-san from Autodesk. Fukuchi-san?
Yep. Yes, so based on the Forge, the inspection workflow is quite simple. With the single sign-on, we can integrate with the BIM 360, the access. We use the access, and then once we capture the photos, the Reconstruct automatically process the point cloud, and with the point cloud, the overlaid on the photos overlaid onto the 3D point cloud. The inspectors, they can use the web browser, viewers to inspect every task. And then the report generated from the inspection result, the specific, the file format, the forms specified by the government can be generated automatically. And the more importantly, this is the inspection, the workflow. For example, in Japan, every 5 years, every bridge needs to be inspected and secure the healthiness of the structure. So we are targeting to integrate the BIM 360 docs to be the ISO 19650 compliant long-term the data management system, so that this is the entire workflow of the bridge inspection using starting from the drone, the capturing, and the remote and the virtual the inspection system.
Wonderful, Fukuchi-san. There are a couple of important points to make here. Again, it's completely agnostic to how images and videos are captured. You upload them and it automatically processes them. It maps that data against your design information, whether that comes from InfraWorks, Civil 3D, PDF documents, or maybe no design information, purely an as-is condition modeling of the asset. From the demo that we showed you, you can see how you'd be able to perform inspection, placing the pins, customize it, which in the case of MLIT with the new guidelines that are being enforced now, this system is really standardizing that entire process at the country level. So now you can document issues, severity of the defects, and use that for your analysis. One of the unique aspects that we've recently worked on with Morikawa-san and Hide-san's team is to automate the process of generating reports. So the number of reports that are specifically required and recommended by MLIT to be created for every infrastructure inspection. Once you pin your information into the system, it automatically generates these reports in form of Excel, PDF, and as we showed you before, you can also generate tickets that can be used as part of a work order system. All that data is already integrated into BIM 360, so we already have that integration in place, and our ongoing conversation, as Fukuchi-san mentioned, has to do with integration with issue management. So issues that are being documented in Reconstruct can also be ported back into BIM 360 in case if you plan on using that information. And this cycle repeats over time. If you come back in 5 years from now, you can redo the new capture, and the AI engine that is embedded into Reconstruct computer vision capability would automatically align the new model against the previous model, even if you don't have any GPS data. Similarities of the scene enables us to do that. So I didn't show a whole lot of examples of how design information can be brought in. So here's just an example. This is a retrofit of an existing infrastructure asset. So you're looking at the 360 video documentation that is mapped into 3D. In this project, also laser scanning point clouds very important into the system, mapped against 3D design information. So what it means is that now you can go into any image view that you desire, and from that image perform your length, area, volume measurement directly from the image, because it's all in 3D, and have your design information overlaid against it. So if your inspection is also accomplished together with an actual retrofit on a job, you'll be able to contrast the design against that. Or if you want to track changes against design over time, this really shows you what is there versus what should be there. So what it all means is now the system organizes photos across a three-dimensional viewer and pins them into a location in 3D. You can dive into every image to see fine details and measure any dimension you want directly from the images. If you look into our Autodesk University handout, we've provided guideline on why image-based inspection is accurate, and perhaps even more accurate than directly using point clouds and mesh models that is being used. So we've done actually a comparative study with a number of experts, and we've shown that with a few order of magnitude, accuracy of measurement can be increased if we use image as the interface. Markup capabilities there, so issues can be directly documented, and as we showed you in the demo, you can continue doing the markup by documenting all asset locations. And again, changes over time would be documented as well. The beauty is that now reports can be automatically generated. They will all preserve online. They can be emailed. They can be text messaged live if you desire to do that. And all of them are really being attached to 3D location. That means if you want to stick to a Word document workflow, you can download them. If you want to generate MLIT compliant reports, you can also download them too. So what does that workflow look like? Oftentimes when it comes to generating reports, once we've done our inspection, we want to take the reader of that report to specific viewpoints. that we've always been generating, right? We want to have a side view, we want to have a section view, we want to have a below deck view where we really show the result of our inspection. So we worked very closely with Nita-san, Murakawa-san to have a workflow that the user can define on most informative views that they want to include in the report. That means, for example, we go to this bridge pier, and then we see there are a number of cracks that are already documented in 3D. What we would do is we would create a specific view. That means we would click on a number of locations and say, from this viewpoint, I want to generate a 2D orthophoto that can be supplemented into the report. So the system runs that view, automatically generates an orthophoto. As much as that information is in 3D, it gives you access to that information in 2D. And once you activate your issues, everything that was documented in 3D would automatically pop up in 2D. You can customize it and can say, in these views, I don't want all the information. I just want to have the ID, element ID, the type of damage, the severity of that. The rest of the information can be embedded into the report, but in this unique view, I want to have that information. So this is now being brought into application to generate official reports by MLIT. For example, this is Form 9 and Form 10 that comply with the new requirements that, again, automatically, once you've done your visual and visual inspection in 3D, you would automatically generate these reports that are 2D oriented or specific images with that information. So what does it all mean? That means with one workflow, you can also improve the process of analytics. All that information is being accessed via the web. Information is being organized in GIS form or can be project cards. It's all being secured on the cloud, and it can be customized. We specifically customize it for MLIT and also a few other agencies that we work with, and migration of existing data is possible because it relies on existing data. You can bring in your old data into the platform and create that historical record of the project that we mentioned before. You can always come back and perform later inspections. You identify an issue, you can mark it up and say, I want to have a team go back and do one more inspection if that happens. So you can go and take new images, generate a new model. The new model is comparable against the previous model, so you can compare before and after. And if you desire to extend the application of this model to be used for operation and maintenance, you can edit that information and store all that within a three-dimensional scene. So what is really the value proposition? This is something that we had the pleasure of working with MLIT to assess. So as Nita-san mentioned, this was a vision back in 2018, but that vision has been realized today. And there are many groups from consultants to contractors to owners that are working with us on leveraging this opportunity. And what that means is instead of having individuals out in the field, we can minimize their exposure to risk and cost by looking into automating the process of capture, bringing that data back into web-based environment in a 3D form. So detection, measurement of the defects can all be done in a three-dimensional scene, have people record them, and automatically generate these reports. And that all really forms the basis of the near future. With this data and integration that we have with BIM 360, it really opens up the room for AI algorithms. Our team and many others are working on automated defect detections. But if you really want to scale it, let's just pick MLIT. You need to make sure that this really works for all different types of defects, 26 different types, and can automatically find severity. And that requires supervised data, as Nita-san mentioned. And this platform being used at a scale, at an industry level, is now enabling us to capture that data. So we're all excited that in next 12 months, we'll be able to bring a lot of those capabilities based on massive amount of data that's being annotated by the experts, and it can be used as a base of training AI engines. It all comes together into that same vision that Nita-san showed you earlier. Now we can go ahead and perform that inspection that used to happen out in the field. We're just limiting that to the imaging process, judgment of the defect type, location, and organizing all that report, all that time consuming this process that we have to spend. And that can all be automated, which are some of the goals that we worked on specifically with MLIT. So again, it gives you an access to four-dimensional reality data, localizes that information, and it gives you that time machine for inspection that you can compare and detect defects and even perhaps forecast them when you tap into AI engine capabilities. And again, it can be customized. So if you have different practices, if you want to migrate your existing data, that would be something that you can specifically work with this Reconstruct engine that lives on Forge capabilities. So what are the takeaways? We've shown you an end-to-end workflow, a unified system. that taps into your existing data to improve the process of inspection. It minimizes double data entry. It minimizes time to generate reports. It makes it more objective and makes it more accurate. You can go back to the data over and over and visually verify every information that's been provided to you. And for those inspectors that want to interact with the data more and more, everything is at their fingertip. They can upload existing information, manuals, recommendations, and store them in a three-dimensional scene as much as they can generate owner-compliant reports for inspections. So that said, that's really our presentation for bridge inspection with aerial robotics that can be supplemented with 360 cameras. And this was really mostly from a workflow perspective. Our contact information is on the web, on the handout for all of us, and mine is here on the screen. We'd be happy to interact with you if anyone has any question. So please feel free to reach out to us. We are excited to bring this capability to the Japanese market beyond what we've already achieved, and also our American partners. Fukuchi-san, any lasting word?
No, thank you very much for the attending this session. So
and I want to also thank on our behalf Nita-san and Murakawa-san, who's been supporting this journey. Doing this at the scale of a country is not a small task, and this is really a vision that Nita-san and Murakawa-san has brought on board. And we, as as an American partner, we've been really excited to be part of this journey with them. So thank you.
Thank you very much.
right, bye.